Hi everyone, this is Oliver, and in this video I'll be presenting the proof of a result that deals with sets with large intersections. So I will prove the following theorem. Suppose A is a measurable set for which there is some C, which is positive, such that the measure of A intersected with I is greater than or equal to C times the measure or the length of I for any interval I. Then the theorem states that the measure of the complement of A is 0. So let's prove this. So to prove this, we will proceed by contradiction. So assume that the measure of the complement of A is not 0, in other words, greater than 0. And by the definition of outer measure, we know that the outer measure of any set is the infimum of the sum of the length of the set of the union of open intervals that cover the set AC. Now, since we know that A is measurable, then we know that the complement of A is measurable. So we can just say this equals the Lebesgue measure of AC rather than its outer measure, because we're dealing with a measurable set. And for the rest of the proof, any of the sets we're going to be dealing with are either AC, or some intersection or union of those with intervals, which are also measurable. So we'll just drop the outer measure symbol altogether and just deal with the Lebesgue measure. So seeing as this is the definition of the measure of AC, then if we're given any alpha in 0, 1, we can find a sequence of open intervals, IN, such that I'll write on the next line, such that alpha times sum of the lengths, the intervals, is less than or equal to measure of complement of A, and this is actually equal to the measure of the complement of A intersected with with the infinite union, the countable union of those intervals. And this is true. Why is this true? Because AC is inside of that union. So this equality here is true. And this itself is by the countable, by the subadditivity, the countable subadditivity of measure is less than or equal to the sum of the measures AC intersected with IN. Right. Good. So from this, we can see that there is some let's call it n0, such that alpha times the length of the interval in0 is less than or equal to the measure of the complement of A intersected with in0. Now, why is this true? Okay, so if we look at the above inequality, the inequality on the line above, we can say that this is true because if we assume the contrary, that the length of in0 is greater than the measure of AC intersected with in0 for all n, for all n, then the above inequality cannot be satisfied because obviously the alpha times the sum of these will be greater than the sum of these. So this is true. Now, we have that the length of in0 is equal to the measure of A with A intersected with in0 plus the measure of A complement with in0, and this is just because those are two disjoint sets that when we take their union, we get in0, so this is true. And now, with the results we have, we can say that this is equal to C times length in0. That comes from the theorem, the statement in the theorem. If we look above, that comes from this. And plus alpha times length in0, and that comes from the line just above, right here. So this is equal to C plus alpha times length in0. Now, however, let's note that it must be that C is in 0, 1. Why is that? Because if we look at the statement of the theorem, the only way that, I'll write it, C times length I less than or equal to A I. The only way this can be true is if C is in 0, 1. And why is that? Because this is less than or equal to the length of I, right? Because A and I is a subset of I. So this is only satisfied when C is between 0 and 1. And okay, so this let's keep this in mind for the next step, and we can show the contradiction in the next step because we can always select an alpha in 0, 1 to make C plus alpha greater than 1, right? Because we know that C is between 0 and 1, and alpha is anything between 0 and 1. So this essentially gives us that the length of in0 is greater than the length of in0. If we just look above right here at this inequality. So that's clearly a contradiction. And thus, we have proven the claim that the measure of AC is equal to 0. And that's it.